AI's impact on science has been in the headlines lately, but the potential for AI to advance science has long been a motivating force for many of us in the field, dating back to the early AI researchers such as Alan Turing and Christopher Lockett Higgins, and to many in recent decades, including my colleagues at Google DeepMind and Google Research. The excitement around AI in science is not because of a belief that AI is a replacement for scientists, but because many of the confounding problems in science benefit from the use of computational techniques, thus making AI a powerful tool to assist the work of scientists. We saw early signs of this assistive capability with the potential in the work of Hodgkins and Huxley's use of computational approaches to describe how nerve impulses travel along neurons, work that would win them the Nobel Prize in 1963. Fast forward to my colleagues Demis Hassabis, John Jumper, and the AlphaFold team, whose work using AI recently won the Nobel Prize in chemistry, solving the protein folding problem, a remarkable achievement. This is a problem that was posed by Nobel laureate Christian Amundsen in the 1970s. So how is AI helping advance science? I'll start with speed. In some areas of science, increasingly capable AI is making it possible for us to condense hundreds or even thousands of years of research into a few years, months, or even days. AI is also helping expand the scope of research, enabling scientists to look at many things at once and in many new ways, rather than one by one. In addition, AI advances, along with the access to the insights from using it, are enabling many more people to participate in research so that we can further accelerate scientific discovery to the benefit of society. Let me share briefly a few examples of how AI is enabling landmark advances, starting with the work of Demis and John with AlphaFold. With AlphaFold, over the course of a year, my colleagues were able to predict the structure of nearly every protein known to science, over 200 million of them. And with AlphaFold 3, they've extended beyond proteins to all of life's biomolecules and their interactions, including DNA, RNA, and ligands. To date, AlphaFold has been used by more than 2 million researchers in more than 190 countries, working on problems ranging from neglected diseases to drug-resistant bacteria. AlphaSense, which builds on AlphaFold, enabled my colleagues to categorize almost 89% of the 71 possible missense variants. These are single-letter substitutions in DNA, and they're able to categorize them as likely pathogenic or benign. By contrast, only 0.1% had been confirmed by human experts, albeit in more detail. When the human genome was initially sequenced, an incredible achievement, it was based on a single genomic assembly. Last year, my colleagues in Google Research, using AI tools and working with a consortium of academic collaborators, released the first draft reference human pangenome. This was based on 47 genomic assemblies, thus better representing human genetic diversity. In neuroscience, a 10-year collaboration between my colleagues in Google Research, the Max Planck Institute, and the Lightman Lab at Harvard recently produced a nanoscale mapping of a piece of the human brain. That is at a level of detail never previously achieved before. This project revealed never-before-seen structures in the human brain that may change our understanding of how the brain works and maybe perhaps open pathways to understanding diseases like Alzheimer's and many more. The full mapping of this has been made publicly available for researchers to build on. Beyond the life sciences, we're seeing progress in other domains. In a landmark achievement for climate modeling, we combine machine learning with traditional physics-based approach to build neural GCM. This allows us to simulate the atmosphere more accurately and efficiently. In fact, neural GCM can simulate over 70,000 days of the atmosphere in the time it would take a state-of-the-art physics-based model to simulate only 19 days. There are other similar breakthroughs, such as the work by my colleagues at Google DeepMind with GraphCast, which is able to provide very accurate 10-day forecasts that are much better than the gold standard in weather forecasting. Our quantum AI team is making progress on questions that were previously the realm of science fiction, like studying the characteristics of traversable wormholes. This opens up new possibilities for testing quantum gravity theories originally posed with the Einstein-Rosen bridge almost 90 years ago. In fact, quantum is an area where we're beginning to see promising bidirectional reinforcement between AI and science. In one direction, AI is advancing our progress in quantum computing, and in the other, quantum is helping advance research in AI. There are many other such examples that we're working on in material science, fusion, mathematics, and more, and in all of these in deep collaboration with academic scientists. Beyond such breakthroughs in science, AI is also advancing science in ways that are already providing tangible benefits for real people in areas like climate change and healthcare. Let me start with an example from climate adaptation. Flood forecasting is a much more frequent and urgent problem due to climate change. And now advances in AI have enabled us to fill large gaps in data to predict riverine floods up to 7 days in advance with the same accuracy as nowcasts. After an initial pilot in Bangladesh, our early warning platform, FloodHub, now covers 100 countries, covering 700 million people with such flood forecasts. And in an example in climate mitigation, consider the following. The formation of contrails, those streaks of white that you see behind airplanes, has long been known as a driver of emissions in aviation, accounting for as much as 35% of aviation's global warming impact. My colleagues in Google Research developed an AI model that predicts where contrails are likely to form, and in partnership with American Airlines, tested this in over 70 flights. We measured the impact and found a 54% reduction in emissions. Similarly, AI offers much promise for disease detection, especially in low-resource communities and countries and regions of the world. For example, 8 years ago, Google researchers found that AI could help accurately predict retinal scans, accurately interpret retinal scans to detect diabetic retinopathy, a preventable cause of blindness that affects roughly 100 million people. We developed a screening tool that's been used in more than 600,000 screenings worldwide, and in new partnerships in Thailand and India will enable 6 million screenings over the coming few years. We've been implementing other examples, including in tuberculosis, colorectal cancer, breast cancer, and maternal health. Despite all this progress, this is just the beginning. There's still so much more to do. I see 3 areas of focus to fully realize AI's potential to help advance science and bring tangible benefits to society. First, we need to continue to make progress on AI's current limitations and shortcomings, and to increase AI's capabilities to be able to assist in developing novel scientific concepts, theories, experiments, and more. Second, we need a sustained commitment to the scientific method, something my colleague Demis Hassabis is always talking about, imploring us to pay attention to, and to also focus on responsible approaches to using AI to advance science. We need scientists, ethicists, and safety experts, like many in this room, working together to address the risks most particular to science, like viruses and bioweapons, as well as challenges like bias in data sets, privacy preservation, and environmental impacts. Third, we need to prioritize making AI-enabled research tools and resources more accessible to more scientists in more places, and to make sure the progress we make from all of this benefits people everywhere. I'm very excited about what lies ahead in all of this and this new era of discovery. There's so much we can do together to build tools that help advance science and benefit everyone. And there's so much we can do to enable amazing scientists, including all of you in this room and elsewhere, in their work. We'll be hearing from some of these extraordinary scientists today.